Next, we move on to data processing. So I imported basically from sklearn model selection import train test split. X is equal to iris drop dot species, axis is equal to 1. What this does is basically creates a data frame X containing like all the columns from the iris data frame except like the species columns as a way to separate the features like the measurements from like the target variable. Then there's the I equals iris data frame equals species. What this does is basically it creates a series Y containing only the species column from the data frame. Then we move on to X train, X test, Y train, Y test, train test. Basically, what this does, it basically splits both the features and the target into the training and testing sets. As 80% of this goes to the testing set, and 20% of it goes to the testing set. So yeah. Afterwards, I printed like the shape of the X train, the shape of the Y train, the shape of the X test, and the shape of the Y test. So the shape for this is like a 120 rows and 4 columns, 120 rows. Testing set's shape is like 30 columns, not 30 rows, but 4 columns and 30 rows. So yeah. Next, we move on to one hot encoding for target variables. Basically, I imported from sklearn preprocessing import standard scale, one hot encoder, label encoder, and polynomial features. So label encounter encoder is equal to label encoder. So what this does is basically converts the string labels such as like the name of the species, such as like siesta, color, and the virgicana into numbers. Then Y train encoded is equal to label encoder dot fit transform Y train. What basically does it fits the encoder to the training labels. Y test encoded equal to label encoder dot transform. What this does is basically applies the same encoding to the testing variables to like ensure like there's like consistency between the training and the testing encoding. And then afterwards, one hot encoder is equal to one hot encoder sparse output false. Well, basically what this does is it just applies the one hot encoding to the encoder labels. Then we move on to Y training, one hot to one hot encoder, the dot fit dot transform. What basically this does is it creates like a binary like vector where each of the class gets its own label with like a one indicating like class membership. For example, like Iris Celeste, so like over here, it gets a one over here, so it becomes 100, and Iris Vericana becomes 011, and Iris Vericolor becomes 010. Then the Y test, then we move on to Y test and one hot equals equal to one hot encoder dot transform Y test encoder reshape dot -1 and 1. So what this does is basically applies the same one hot encoding to the test labels. Then we print out the labels, then we print out like the first 5 samples using this for loop over here. So these are like the first 5 samples of all the M1 high encoding. This is the encoded, so 0 is like equal to the iris siesta, and then that's the 1 hot, which is like 100. Then iris vericana is encoded as 2, and its 1 hot encoding is equal to 001. Then encoded for iris vericolor is encoded 1, and its 1 hot is 010. So yeah. Then we move on to 1 hot df is equal to pandas data frame, which inside has Y train 1 hot and columns equals to CLC for CLC and label encoder dot classes. So basically what this does, it basically creates a pandas data frame called named 1 hot data frame using the same encoded target variables like y train 1 hot. Then it prints out all the 10 samples for this, and then I used head 10 to get the 10 samples. So 0 is like iris ceratana, as this has the 101. Next one is iris vericana, as is 001. The next one is iris vericolor, so this is 010. So yeah. Next, we move on to creating polynomial features. So poly is equal to polynomial feature degree 2 include bias false. Well, basically what this does is it creates like an instance of a polynomial feature transformer, and setting the degree to 2 creates like a reasonable balance between like the model complexity and the interpretability of it. Then we move on to x train poly is equal to poly fit transform x train. So what this does is basically it learns the polynomial feature structure from the training data and applies it to the transformation, and then x test poly dot transformation x test. What this does is it basically applies the same transformation to the test data. Then we print out the x train shape and then the x train poly shape. Then we move on to the features name. So features name is equal to poly.get features names out x.home. So basically what this does is it basically retrieves like readable names, human readable names for the all created polynomial features using like the original columns names. Then we move on to polydiff is equal to p pandas data frame x train poly to the fifth columns is equal to feature columns. Well, basically what this is, like, it basically creates like a pandas data frame with the first 5 samples of the transform data. Then we print out the first 5 samples and the first 10 features using this poly data frame.iloc is equal to this, and then we print out all the polynomial feature names by printing out feature name. So from my data set, we can tell the original feature shape has 120 rows and 4 columns. However, as the polynomial feature shape has 120 columns and 14 rows. So the 14 rows that got updated. So those are like the 4 original features, such as like the spatial length, the spatial width, the petal length, and like the petal width with a combination of them being squared, so spatial length being squared, spatial width being squared, petal length being squared, and then petal width being squared, plus like the 6 interactable features, such as like the spatial length times the spatial width, and the spatial length times the petal length, and then spatial length times the petal width, and then the spatial width times the petal width. So that's the reason why there's 14 rows now as opposed to 4. So these are all the samples for like the 10 features. So these are all for the spatial length, spatial width, petal width, the petal width length squared, spatial length times spatial width, spatial length times petal length, spatial length times petal width, spatial width squared, and spatial width times petal length. So yeah, and these are all the polynomial names as I mentioned. So these are like all the 4 spatial lengths and then till like petal width. So yeah. Next, we move on to scalar is equal to standard scalar. So basically what this does is it basically standardizes all the features. Next, we move on to x train scaled is equal to scalar that'll fit transform x train poly. Well, basically what this is, for each feature, it basically subtracts and like divides it by the standard deviation. And then x train scaled is equal to scalar transform x test poly. Well, basically what this does is it uses the same mean and standard deviation calculated from like the training data, and it basically applies the same transformation but to the test data. So yeah. Then we go on to printing. The mean and standard for like before scaling it and then after scaling it. So before scaling it, we see that all of these numbers are like very varied. So they're not like close to each other, as they're not on the same scale, and their standard deviation is also not that close, as there's very varied. As opposed to after scaling it, as now all these features have the same scale, which is ideal as for many machine learning algorithms, as features on different scales cause like some features to like dominate over the other, which is pretty bad. So yeah. Then we move on to scaling data frame is equal to pandas.dataframe. X train is equal to s scaled with columns is equal to feature name. Basically, what this line of code does is basically it selects the first five samples from the scaled training data, and now all the values are basically being centered around 0. So now these are now all the scaled features around here. So these are the scaled features. So the spatial length, the width, the petal width, and so on to like spatial width times petal length. So yeah. Next, we move on to visualizing the effect of scaling with a box plot for the 10 features. So this creates basically a new figure with a size of like 15 inches by width times 6 inches by length. So what this block of code does is basically plt.subplot121. What it basically does is it basically divides the figure into one row and two columns and selects the first subplot on the left side to plt x ticks, range 1 to 11, and then feature names, and then this shows the original distribution of the features before standardization, as each one has the different ranges and different scale. And then PLT subplot to PLT tickets, range to 1 to 1 till here. Basically, this shows the standardized feature distribution, as now all the features have the similar scaling. Here's the visual of this. So before scaling, all these have different ranges and are not consistent with each other. However, after scaling, they're very similar in range. However, there are a few outliers, but that should not matter as much.